And now we're going to use our last 3 days to look at some applications. And all the applications, were computer science oriented. So these are the these are the slides here on the computing. And so the first section, computable and uncomputable, we've done a few times. So we're going to go down and do time complexity and classifying functions. I'm not really clear how much of this you've done already. You've probably done it in, if you've taken 2011, you've done it. And if you've taken probably 2030, those first year programming courses, what are they, 1030, 2030? Anyway, this is going to be from a logic point of view. So holler if you're not following what I'm saying. All right, so we're going to do time complexity. All right, so at the beginning, Euclid came up with the first algorithm, and he just wanted to know, do we know the algorithm or not? Then Turing talked about, is it computable or not? Then this is my father here. This is me here. He's kind of given credit for talking about, is a problem in polynomial time or exponential time. So here are some various time classes. I stole these signs from when I teach it in, what do I teach? That 2011, the data structure course, right? Constant time is the time doesn't grow with your input, right? You have a computer program and its running time doesn't grow with the input, versus log n is the time for binary search, versus linear, linear is the time it takes to look at the input, right? N log n are your fast sorting algorithms. N squared are your slow sorting algorithms. Some polynomial time, n squared into the cube, into the eighth. That's what my father defines as to be a feasible algorithm. Even if it's into the million, it's rare that there's an algorithm into the million, but it's considered to be feasible. As opposed to exponential, exponentials quickly grow to be bigger than the number of atoms in the universe, so it's unfeasible. And then, as we said, there's what's computable or not computable when you don't have a limit, when you don't limit the time. All right? So here's what we plot is how big is the input versus what the running time. And constant, here we call constant, right? The time doesn't grow, right? Versus log n, versus linear, versus n squared, versus 2 to the n. Here's just a little table. You can see, oops, it went by fast. You can see that for inputs of various sizes, how big the running time is, right? So n cubed, when your input gets to be 1,000, right, then n cubed is still 1 billion. So it's not like that's trivial, right? An input of size 1,000 n cubed is still a billion, but on exponential it's 10 to the 300, which is just bigger than anything you can imagine, right? So we're going to talk about how do we write in first order logic that our computational problem is computable in constant time or polytime or exponential time. How do you say things like the class of computational problems that are solved in exponential time is strictly bigger than the class that solves in polytime? All right. So you've seen these before, right? We got problem algorithm A gives the right answer to problem P on input I versus the running time of algorithm A on input I versus some function. T of n could be n squared, right? So how do we say this is what we've seen before? This says that P is computable. There exists an algorithm, a machine that can compute it. You fix them in one machine and then given any input, the machine gives the right answer to the problem, right? Holler if you're not following this. How do we say it's done in n squared time, right? We can add that the running time of the machine on the input is at least n squared, right?
Sir?
Now, you might, right? So this is just saying, in addition to solving the problem, it can use at most n squared time. Then people might ask, what is n? Well, n is considered to be the number of bits to write down the input, right? So that's the, I spent a lot of time on how do we measure size in various other courses, but the classic is how many bits does it take to write down the input? So here, what we're saying is that the running time is a function of the number of bits. So you take the number of bits and you square it, and that's how much time you're allowed, right? So how then do you say a computational problem is not solved in n squared time? And I've given this as various assignments, various test questions, and students always have a hard time doing it. So they might say, for every algorithm, if the algorithm solves the problem, then the amount of time the machine takes is at least n squared, right? That makes sense. I'm not saying that that's a bad answer. It's certainly an intuitive answer. It just doesn't happen to be a logically good enough answer, all right? Here we tried again for every machine and every input. If it solves the problem on that input, then the time is at least n squared, right? Or we could say for every machine, if the machine solves it for every input, then for every input, the time is too big, right? So all of these sound pretty good. Are people following these sort of statements? Yeah. But, my bet is you don't see what's wrong with them, and that's reasonable. So, so I'm going to explain to you why these are false, right? So here we're going to design the, I don't know why I have n squared there. I mean n cubed. I don't know why the n cubed's here, but let's explain why this doesn't say what we want. All right. So for every, right, how do I prove that this, right, is false? All right. Well, so anyway, here I give you an algorithm. Then we make sure that the first. How do you prove that this, right? How do you make this thing false? You have to come up with an algorithm in which the left side is true and the right side is false. Oh, I know what we're saying. We're trying to say it's not computable in n squared algorithm, in n squared, right? So if a problem takes n cubed time, then this should be true, right? Because if it takes n cubed time, then it can't be solved in n squared time. So these statements should be true. And I'm going to show you how I can make these sentences false, which means they're not saying what they're supposed to be saying, right? They're supposed to be saying, if I can solve it, then it takes more than n squared time. Well, here's a problem that does take n cubed time, and I'm going to make this sentence false, right? I make it false by coming up with an algorithm for which the left-hand side is true and the right-hand side is false. Meaning is that I come up with an algorithm that does solve the computational problem, but according to this definition, doesn't take n squared time. Doesn't take more than n squared time. All right, so here what I'm going to do, come up with some funny input, right? Here's just one funny input. It's a bunch of zeros. Why did I make it long? I made it long so that my n squared, right? Here I'm using a number of bits to write it down. I want a little bit of time. I want my n squared to be a little bit big. And there's some answer on the required problem. We have some required problem, and on this input, there's some required answer. And so I'm going to design a machine, an algorithm that does the following, right? If the input to the machine is exactly the input that I care about, then I'm going to do no work whatsoever, right? And I'm going to immediately just return the answer, right? Otherwise, well, I'm assuming that this problem is computable, so it can computable in cubed time. So I'm going to take all my time in the world, and I'm going to solve problem P and give the right answer, right? So what does this mean here? This problem, would you agree that right, for my machine, this says for every machine, and I'm coming up with a machine in which it's false, right? So it's not true for every machine, because here's some machine which is false. And what is it saying? Well, it's saying, well, the left-hand side, we want to make it true. Well, does it solve the problem on every input? Yeah, it solves it on these funny inputs, and it solves it for non-funny input, right? Now, what about the right-hand side, right?
Professor?
Yeah.
I want to ask a question. So you said I equals to a bunch of zero. So
Yeah.
what does this I squared means?
Oh. So one thing that you should know is if well, we could go back, but what do we mean by the size of the input, right? What's our running time? Our running time is the number of bits to write I down, right? So suppose the input is 1, 2, 3, right? Is 10 bits. And then so the quote size of the input is 10. So I square 10 and I get 100, right? So the running time that I'm allowed is we're claiming that the running time is bigger than 100, right? Does that make sense?
Yeah. Thank
right?
you.
And so now what I'm trying to prove is that even though this problem always solves the problem, well, it's not the case that it takes more than 100 times on every input, right? This says for every input it takes 100 times. Every input it takes 100 times. Well, it takes 100 times on most inputs, all inputs but one, right? I've just made one input. Here's one input on which all I do is I read the input, I check to see if it's the right input, I output the right answer, right? So how much time does that take? Well, I don't know. It's less than 100. Right? Does that make sense? So that makes these things false. So they don't say P is not computable in n squared time, right? Because here's a problem that can't be solved in n squared time, and the sentence is false, right? Are people following that?
Can I ask you a question?
Yes, of course you can.
So if we change that input, the I prime, like as a maybe 5, but then that's going to be 25, but then all input is going to be also changes. So wouldn't it change the whole statement? Because you just said...
There's nothing special about this input.
Right.
The reason I made it long was to make sure that I said, how long does it take to check if my input is this and to output the answer? I don't know. I figured, I don't know how you're measuring time, but, right? I figured it could be done in 100 time steps. So I made the input of size 10 so that 10 squared was 100. I'm not sure. Am I getting your question? There's nothing special about this input.
Okay.
Right?
Okay. I'll try to understand it.
Right? It's just here. Let me say it again. What do all these sentences say? And more or less, they're trying to say, if an algorithm solves your computational problem, then the algorithm always takes running time more than the size of the input squared, right? And I'm just saying, well, here's an algorithm. It's a dumb algorithm, right? It just happens to get the right answer quickly on one input, right? So am I claiming this algorithm solves the problem in n squared time? No, it doesn't, because the problem can't be solved in n squared time. But it's not the case that for every input, the running time is too big, right? Because I have one input in which the running time is not too big. Does that make sense?
Yeah, so we just find an instance in which the input we were not able to solve the problem, and once we do that, we essentially prove it's not computable, right?
No,
Like once you find one instance,
no, man. It is computable.
Mm.
It's computable, and you got it completely backwards. All right.
Mm-hmm.
What we want to be able to say a problem here. How do we say a problem is computable in n squared time? Right? We say there exists a machine that can compute it in n squared time. Why? Because for every input, it gets the right answer, and the running time is at most the size of the input squared, right? Or the size of the input is bits. Everybody get that? Right? So now, how do you say P is not computable in n squared time? So what do we want to say? We want to say, think of some problem, satisfiability. I don't know, some problem that's not computable in n squared time.
Okay.
We want to say it's not computable in n squared time. So what you want to say is, well, for every algorithm, it doesn't solve it in n squared time. Right?
Okay.
Well, what do we want to say is, well, if the algorithm solves it, right, there certainly are algorithms that run in less than n squared time, right? They don't do anything. But we want to say if it solves it, then the running time is bigger than n squared.
N squared, okay.
Right? That's what we want to say.
Mm-hmm.
Right? We want to say for every algorithm, if the algorithm solves it, then the running time is bigger than n squared. Right?
Mm-hmm.
Now, I am claiming that takes some problem that takes a lot of time. Right? It's computable, but it takes a lot of time.
Mm-hmm.
Right? So our sentence that says problem P is not computable in n squared time should be true, right? Because we're coming up with a problem P that can't be solved in n squared time.
I have a question.
So, but I'm going to prove that these sentences are false, right? They're supposed to, when P is not computable in n squared time, they're supposed to be true. All right. So what is my algorithm? My algorithm, what do I have to do to come up with it? I have to come up with an algorithm. How do I prove this is false? Right? I prove it's false.
Jeff, couldn't you have done the same thing for your the problem that you're saying that like there has to be an algorithm? It's for sure going to take longer than n squared time. Can't you take the same approach where you say, like, you set up the machine in such a way that it's already almost set up, it's like expecting the solution?
Yeah,
you know what I mean?
Exactly.
So there's no solution then for all.
Yeah, I think you're getting it, that this isn't good, right? I'm going to come up with an algorithm. I'm going to show that my algorithm solves the problem for every input. I'm going to show that it's not true that for every input, the algorithm takes too long. All right?
Okay.
Why? Because I'm going to have one input, one weird input where the algorithm just happens to be fast. All right? We can design, given an input, we can design an algorithm that's fast on that input, right? We just have it output the right answer on that input. All right, so now what's the problem? The problem is that this algorithm does solve the problem on every input, right? It does. But is it true that for every input, it takes a lot of time? No. It takes a lot of time on every input except for one. On my weird input, it takes too much time.
So that's because it's all machine. Is that why it make it incorrect statement? Is that why it makes it false statement?
Well, this is claiming for every machine.
Right.
And in order to make it false, I only need to come up with one machine that makes it false. Right?
Right. Okay.
So what's my machine? Here's my machine. What it does is it just happens to know the answer for this weird input. Right?
Right.
That's all. It's a really slow, bad algorithm. It does solve the problem, but it just happens to get the right answer on this weird input. So what do we know about now? What do we know? Well, is it true for all machines? No, here's a machine for which it's not true. Why is it not true? Well, it does give the right answer on every input, right? And it doesn't run slow on every input. Why doesn't it run slow on every input? Because there's one input on which it runs quickly. Yeah, this is the kind of thing that in upper years I need people to be able to understand, right? This is just, what does it mean for a problem not to be runnable in n-squared time, right? And this is just showing you how it can be subtle, right? What would you say the running time of this, right? What's the running time of this algorithm? Well, it's slow on every input except one, right? So I'm going to call the running time slow, right? Everybody agrees the running time of this algorithm is slow, right? But is it true that on every input, the running time is slow? No, it's not slow on every input. Why? Because there's one input in which it runs fast. All right. Let me try the next slide and see if it helps. All right. What do we want to say? This is in contrast. What do I want to say? Well, if this up here says that it's computable in n-squared time, let's just take the negation of it, right? What's the negation of exists the machine? It's for all machines, right? If there doesn't exist a machine that works for every input, then for every machine, there exists an input, right? There exists an input of what about this input? Well, for this input, either it gives you the wrong answer, right? Or it takes too much time, right? All we have to do for it to fail to compute the problem, we need one input in which it doesn't compute. To fail running time, right? Here, we don't need it to be slow on every input. We just need one input in which it's slow. All right? So here, right? So let's understand it, right? We're trying to say P is uncomputable in n-squared time. Why is it uncomputable? It's uncomputable because every machine fails to compute it in n-squared time, right? There's no machine that computes it in n-squared time. Why is that? Well, because given any machine, it fails to compute P in n-squared time. Why? Because for it to compute P in n-squared time, for every input, it must get the right answer and run in n-squared time, right? For it to fail, there only has to be one input in which it fails, right? All right, so why does it fail on this input? Well, either because it gives the wrong answer or because it takes too much time, right? Does that make sense? The difference between what I have here and what I had on the previous page is on the previous page had for all inputs, right? And I'm not claiming it fails for every input. I'm just claiming that there's at least one input in which it fails, right? Does that make sense? Right?
Yes.
So how would we prove this? We would play the game. You know, I'm all about the game, right? You could do, George would do some sort of formal thing on this, which won't, I don't know, to me doesn't help. For me, it's about the game. How do I prove this is true? Well, the adversary gives me an arbitrary machine. I'm claiming no machine can solve the problem, right? That's what I'm claiming. No machine can solve this problem in n squared time. How do I prove it? Well, the adversary gives me an arbitrary machine. I say, let n be an arbitrary machine. Sorry. I've been cleaning the basement and my lungs are filled with dust. All right, so the adversary gives me a machine, and what do? I come up with one input in which it fails, right? I only need one input in which his machine fails and his machine doesn't work. Why does this machine fail? Well, either it takes too much time or it gives the wrong answer, right? All right, so everybody get that? So
Yeah.
now let's do the same for constant time, all right? So Gödel might get involved in here, right? Because we're just saying Gödel is our logic guy, right? So we want to say a problem is solved in constant time if its running time doesn't depend on the input, right? If the running time is always 5 as the input grows, right? We say that's constant time. All right. So here's a graph. It's a graph of a cosine wave that I got from that alpha, whatever that program is, right? Here's the size of the input. Here's the running time. All right. Is this running time constant? Right? You might say, no, look the running time goes up and down. The running time depends on the input, right? You might say, oh, look it's not constant time because the running time depends on the input. Yeah, but I just needed to be bounded by a constant, right? On every input, the running time is at most 3. That's good enough for me, right? The point is the running time doesn't grow, right? So all we need for it to be constant time is not that the running time doesn't change. We need it to be bounded by a constant, all right? So here we say it solves the problem and the running time is at most c, right? But for what c? Does c have to be 3? Can c be 1,000,000? Can it be 1,000,000,000? Can I say the running time never exceeds 1,000,000,000,000,000, billion? Is that meaningful? Well, yeah, I'm going to say it is meaningful, right? Here, how do we write it? Have people seen the notation big O of 1?
Yeah.
Right, have you seen that?
Yes.
Yeah. So what does it mean, big O of 1? Is this function here big O of 1? Yes, it is, because it's bounded by a constant.
A constant.
Right? The big O means it's less than or equal to a constant. All right, so we're not saying it doesn't depend on an input. We're saying it doesn't grow with the input. Now, who chooses the C? Right? There's a prover who's trying to prove that your problem is computable in a constant time, right? Does he choose the C? Or does the adversary get to choose the C? The adversary who's trying to make this sentence wrong. Well, certainly the adversary would love to choose it, right? He would like to say the constant needs to be 5. Well, what happens if you come up with an algorithm and its running time is 6? Surely 6 is good enough. Who gets to say C is 5? Well, maybe C is 7. Is 7 good enough? Right? So the adversary doesn't get to choose it, right? We're not saying it's bounded by every constant. We're saying it's bounded by some constant, right? It's not bounded by C equals 1, right? Now, the adversary says, oh, Is it fair to have C be 1,000,000? Well, there's a good question. If your algorithm never takes on every input, doesn't take more than 1,000,000 steps, is that good enough? Well, yeah. If it doesn't depend on the input, as the input grows and grows and grows and grows, the running time never gets to be bigger than 1,000,000, then that might be good enough. All right. So so we get to choose the constant C. We could even choose the C to be 1,000,000. All right. Now you might think, when do we choose it? Remember, I used to say compile. Yeah, compile. Not compile time anymore. We call it coding time, right? The coding phase versus the execution phase, right? Do we come up with a constant before the input or after the input?
Before the input?
Before, because the whole point is we don't want the running time to depend on the input, right? So there, for every input, I can have a different constant, right? If the input is really, really big, I come up with a really, really big constant, right? The input's even bigger, I come up with a bigger constant. That's no good, right? What do we want to say? We want to say for every input, we don't want every input to have a different running time, right? We want one constant, right? So we put it here. We say at coding phase, or in the coding phase, I get to design the algorithm and I get to design the constant, right? I can say my algorithm runs in time 5, or my algorithm is bounded by 1,000, or it's bounded by 1,000,000. I get to choose the constant. I can even say my algorithm is bounded by 1 billion if I wanted to, right?
Yes, sir.
Right. But I have to fix it when I fix the machine. Question.
Sir. Sir, I have a question.
Yes.
So for this game, the adversary chooses C, right? The adversary chooses the constant.
No. The prover, the guy who comes up with the machine, chooses the C.
Okay. What does the boss do in this? The boss?
Well, we killed the boss. Why are you asking about the boss?
Okay.
Okay. The boss, who the boss would be is P. What are our free variables? Right? The N's bounded, the C has a bound, the I has a bound, right? The only thing that's free is P.
Yeah.
So the boss would tell us what problem we're talking about.
Oh, okay. And the prover decides what C is, right?
Yes. So,
okay.
Right? During the coding phase, the prover will come up with the machine and come up with a constant C. Right?
Yeah, okay. Thank you.
And he does it before he knows the input. All right, so let's play the game. Let's see if it seems like a reasonable game. Right? Oh, do you like the boss? There he is. You were so right. There's the boss. The boss. Oops. Here, I lost where we were. Where are we? Dear. That was bad. I didn't want that to happen. We are doing time complexity. We are here. Right? No, we are down here further.
Yeah, a bit more down, yeah. We'll be a bit more down. Here, this one, yeah. We were in this one, I believe. The one after this slide.
You might have asked the boss, because maybe she's the boss woman.
Yeah, I saw
we brought her in not as the boss woman, but the woman who helped us understand what it means.
Yeah, I saw the boss icon there, so I was thinking, what if the boss plays a part
here? So
here?
as the boss woman, she was helping us understand what this means, right? But what does she do as the boss? She just tells us the P, right? This is funny arrow. This is blue, so it's really the prover talking. Sometimes I don't get my arrows right. I make a lot of slides. His arrow's wrong. All right. So what does the prover say? The prover says, I'm going to come up with an algorithm, a Turing machine to solve the problem, and I'm going to tell you my constant C, right? Maybe he comes up with a really big C, right? And then what does the adversary say? Wow, adversary says, that's a big C, right? You can do anything with this C, right? It doesn't seem like it's a fair game. But then the adversary realizes that it's okay that the C is so big, right? Because it still needs to work for every input. This is a theoretical thing. We're not saying we actually practically have to do this, right? Has to work for every input. So here we're saying for all inputs. So if the prover comes up with an input that's this big, then the adversary will come up with an input that's even bigger, right?
Sir?
Yeah.
So the adversary gives a bigger input, like for this game, right?
Yeah.
Okay.
Right?
Right?
So it still means something to say, let's say this is a billion. I don't know how many zeros there are, right? I'm saying I can solve this problem in a billion time, no matter what the input is, right? Well, what happens if the input is a trillion?
Then the adversary will give a bigger input,
solve it
right?
in billion time? Maybe not. Right? Does that make sense?
Yeah, I understand.
Right?
I think
we didn't want to say C could be bounded, right? We didn't want to say constant time means you can do it in time 10 or time 100. Who says what 10 or 100 is, right? Maybe we're measuring time in billionths of a second. So this is actually a reasonable running time, right? Nanoseconds. Maybe this is time is run in nanoseconds. So this is a perfectly reasonable C. Right? Does that make sense?
Okay, sir, I wanted to ask one thing. So
Yeah.
for this problem, the adversary's job is mainly to give a bigger value of C, right?
Whose job? The adversary's job?
Adversary, yeah.
Oh, no, dude. Come on, you should know the game by now. The prover comes up with the C. The adversary comes up with a bigger input.
Oh, okay.
Right?
Yeah, okay.
How do we play this game? The blue guy says, I have a machine and I have a constant. And I'm claiming my machine solves the problem in time bounded by my constant. And my constant might be really big. My constant might be a billion, right? But it has to work for every input. So
Yeah.
the adversary then gets to know the constant, right, and gets to come up with an input that's so big that the running time dominates your constant.
Okay.
Right?
Yeah. I understand now. Okay. Thank you.
All right. So this is my father saying what's feasible, right? He says it's a problem is feasible if it can be solved in n squared in polynomial time, right? Polynomial means n to some constant. So how do we write that? We write it the same as we did before. There exists an algorithm. Why can it be solved in polynomial time? Because there exists an algorithm that can solve it in polynomial time. Well, what's polynomial? Into some constant. Which constant? Well, there exists a machine and some constant 5, and we're saying it can be solved in into the 5 time. What does that mean? That means for every input, it solves the problem, and the running time is at most into the 5, right? Polynomial is into something, right? So it's bounded by into some constant, right? People buying this? Which C? Again, during the coding phase. Here I remember to change it from to coding phase, right? During the coding phase, he can choose any C he wants, right? But then but the adversary then makes the input bigger, right? If I'm claiming it can be solved in poly time, if I say it's the running time is into the 100, if you came up with an algorithm that solves satisfiability and it worked in into 100 time, people would be really, really impressed. All right, because they believe it takes exponential time. All right, which n big N. N is the number of bits to write down the input, right? Oh, so that's just doing what we did before, right? Here's everybody got the definition of polytime? All right.
Can you say it one more time?
Yeah. Suppose I want to prove to you, you're my boss, you give me computational problem P, right? And I want to prove to you that P, you say, hey, I want to solve this computational problem for my work, right? I'm going to say, no problem, dude, no problem, boss. I can solve it, and I can solve it in polynomial time, right? So how do I prove that to you? Well, I prove it to you by giving you an algorithm, right? He's not going to be convinced until you give me an algorithm. I give you an algorithm, and then I give you a constant C. Maybe I claim my running time is a polynomial. Which polynomial? Well, my algorithm, it could be right here, which it could be n squared, it could be n cubed, it could be in the fourth, into any C, right? So I'm going to say my algorithm runs into the 5 time. So I'm going to make C be 5, right? I go into work, I say, here's my code, my algorithm runs into the 5 time. So then the guy who doesn't like me, my adversary, comes and says, I don't believe that your algorithm runs into the 5 time. I'm going to say, yes, it does. He says, no, it doesn't. All right. So what do? We run it. So he comes, if he says it doesn't, so what does he have? I have to then say, you don't think my algorithm runs into the 5 time? Oh, yeah, give me an input. So the adversary gives me an input. I'm claiming it works for every input. He claims it doesn't. So if it doesn't, he gives me some input in which it doesn't work fast enough. And we run it. And look at it stops, it gives the right answer, and the running time is at most the size of the input raised to the power of 5. So I win. And my boss gives me a raise. Right? Everybody understand that? That's the way it's going to actually work at your company, right? You get a job. This is actually the game that's going to play, right? Does that make sense?
Yes.
It's not a theoretical, it's logic, but it's talking about the game that you're actually going to play at work, right? You're actually going to have to come up with a machine. You're actually going to have to give me the constant, and claim it runs into the 5 time. And then you're actually going to have to get an input from somebody who's playing nasty to you. And your program is going to actually have to get the right answer and actually run in the right amount of time. Right? All right. So now what about exponential time? If it takes exponential time, then we say is infeasible. Right? What do we do then? Well, what is exponential time? Well, it could be 2 to the n could be exponential. What about 1.001 to the n? Is that exponential? Yeah, if n grows big enough, this is going to start growing exponential, right? Right? What about 3 to the n? Is that exponential? Those are all exponentials, right? Well, what we're going to do is we're going to convert. I don't know if you know how to do this. You take the log base 2 of 1.001, and what you get is 1.0014. And so these two numbers are equivalent. You should be able to, if you don't know that, you should learn that, or I can help you with that, right? What about this? 3 to the n is the same as 2 to the 1.58 times n. Why? Because 1.58 is the log of 3. I don't know. Play with logs and figure out that this works, right? So what we're going to say here, and all our C's, I keep writing C here, but C has to be greater than 0. All right, that's a requirement on C. When I say there exists a C, I mean there exists a C greater than 0. All right, so here we're saying the running time is bounded by 2 to some constant times the size of the input. And you might ask, why do I put a 2 here? Well, it doesn't really matter. I could put 2 as a common base. People sometimes put 10, sometimes put E, but the C is what allows you to change base.
Sorry,
Right?
Professor.
Yep.
Can you define what infeasible means?
Yes, it means it takes exponential time.
Wasn't it infeasible for polynomial time too?
No, that was feasible. It's
Okay.
the N. The N that makes it not feasible. Not feasible. Infeasible means not feasible. Right?
That just means bad, basically.
Which is bad. Means it's probably going to take more time than the number of atoms in the universe to solve it on every input.
Okay.
Right? Right. So here
I have a question.
Yeah.
Let's just say it takes factorial time. Would that also be infeasible?
Yeah. N factorial is about n to the n. So that's bigger than 2 to the n.
Okay, thank you.
Hey Jeff, so anything that is feasible is at least lower than at least polynomial at the most polynomial time, or less than.
Yeah.
Constant can be also feasible too.
Yes.
A constant time.
Yes.
Okay, that makes sense.
Right. Everybody getting that? If it runs an exponential time, then maybe on some inputs you can hack together an answer, but generally you can't. Right?
Do we have to define C to be a finite constant? Because if C is infinite...
No, C can't be infinite. That would be dumb.
Right, but we haven't defined it to not be infinite.
What?
Well, we haven't said it isn't infinite. We just said it's a number.
And tell me an integer that's not finite.
No, I'm just asking, like, do we have to define C not to be infinite, or is that just something that we're assuming?
Things don't all fit on the page. So when I say exists C, I mean it's a real number that's finite and bigger than 0.
Okay, thank you.
Yeah. Everybody good here? Now, let's be a little bit more precise. I suppose that your problem takes a certain amount of setup time, right? Maybe the running time is nicely n squared, but only when the input's reasonably big, right? So here you can see, we're plotting running time. This is the size of the input versus the running time, and you see here that there's some initial time that, right? So for small inputs, the problem is the size of the input to the C is small, right? Remember, why did I make my input in that one example have 10 bits in it? Because I wanted 10 squared to be at least 100, so I had some time to do some basic setup, right? So if the input's too small, then this running time is too small. And that's not what we're talking about. We're talking about, for all inputs, what we mean as inputs get really, really big. We don't really care about the running time on small inputs, right? If it takes some little setup time, we don't care, right? So how can we fix that? We can add on some constant which allows us setup time. So when the input's really, really small and this disappears, we still have a constant here to allow us setup time, right? So that's one way you could do it, but it's not the standard way to do it. The standard big O way of doing it is we only care about inputs that are reasonably big, right? We say for sufficiently big inputs. So if the input is smaller than some bound, then we don't care about its running time. And then again, now who chooses those? Again, you choose them all at the beginning before you know the input. All right. So how do we say a problem is not computable in polytime? All right. This is how we say it is computable in polytime. So how do we say it's not computable in polytime? Well, we just take the negation, right? If it's not true that there exists an algorithm, then for all algorithms fail to solve it in Pauli time. Why? Because all constants, oh, that is a typo.
Yeah, I was gonna say, is that?
So here, let's fix our typo here. All right, there. Typo fixed, right? For all constants, here I had to switch from exist to for all, right? I switched from for all to exists. Everybody see that? And here we switched from or to and to or, right? We switched from equals to not equals, from less than or equal to greater than equal, right? That's how you take the negation, right? Now we have these complexity classes. We have problems that can be solved in Pauli time, problems that can be solved in exponential time, right? And what do we want to say? We want to say that there are problems who live in here, where my cursor is. What does that mean? It means problems that take exponential time, can be done in exponential time, but can't be done in Pauli time, right? We want to say there are problems that can be solved in exponential time, but not in Pauli time. So how do we say that? Here, that's where our P is, right? Our P is living right there. We want to say P is computable in exponential time and not computable in Pauli time. So we write it down just like this, right? The first line, right, is saying what? It can be done there exists a machine that can solve it in exponential time, right? However, for every machine, it won't solve it in Pauli time, right? I just said the one sentence and not the other sentence, right? Everybody get that?
Sir.
Yep.
So for some, it will solve in exponential time, but for all, it won't solve in Pauli time, right? That's what you meant, right?
Yeah, exactly.
By the two statements there, okay.
Yeah, the two statement. Here it says, there is a machine that can solve it in Pauli time, in exponential time. That's why the P is in this green circle. It's in the green circle because there's a machine that can solve it in exponential time, right?
Yeah.
But it's not in the purple circle, right? Why? Because for every machine, it fails to solve it in Pauli time.
Oh, all right. Okay.
Right?
Yeah. Okay, thank you.
Hi, Professor.
Yeah.
Can I ask the exist C is for or C?
I fixed that on the one page, and then I didn't fix it again.
Oh, okay, that makes sense. Thank you.
Yeah, that was a typo. You know, you make 1,000 slides, there's got to be typos somewhere.
Yeah, I understand. Yeah, just want to clarify. Okay, thank you.
Yeah, for sure. Right? It's good to check, because then that was good, because it got me to fix it on the next slide. All right, so here, right, so then we say, well, which P are we talking about, right? The boss is giving me the P. What we're saying here is there are problems, right? We're saying these two classes are not equal, right? What you can do in Pauli time and what you can do in exponential time are not the same class. Why? Because there exists a problem. We can prove. It's way beyond the scope of what we're going to do today. But I could prove to you that there exists a problem that can be solved in exponential time that can't be solved in Pauli time. Right? All right. That means the one computational class is strictly bigger than the other class. Right? All right. Are people good with that?
Yes.
So let's do it again.